Today, I'm going to introduce our work Unmixing Before Fusion, a generalized paradigm for multi-source-based hyperspectral image synthesis. In the realm of AI, data serves as a pivotal resource. Real-world hyperspectral images, bearing wide spectral characteristics, are particularly valuable. This results in a significant data scarcity and class imbalance problems, impeding large-scale AI-based HSI applications. HSI synthesis offers a viable solution to solve the data shortage problem. Existing HSI synthesis techniques, such as physical modeling-based, affine transformation-based, or the spectral reconstruction-based methods, have their merits. They also grapple with significant limitations, such as lack of authenticity, restricted diversity, and inability to produce new samples. To address the issues, this work proposes a new paradigm for HSI generation, unmixing before fusion. We conduct the customized unmixing across multi-source data to bridge their dimensional gap and release the burden from high dimensionality. By fusing unpaired multi-source data, the method can overcome the limited sample availability. Moreover, the proposed paradigm can be generalized with various generative AI models for HSI synthesis to generate abundant, diverse, realistic samples. The method is motivated by a key observation. Similar scenes share common low-rank features that can be described by a few end members. Under this observation, we can generate abundance and sharing the specific end member, bridging the dimensional gap between RGB and HSIs in the abundance space. Consequently, we can fuse unpaired multi-source data, enabling model to learn various and realistic spatial distributions. Specifically, the overall framework includes two stages. First, we conduct the unmixing decomposition on HSIs to estimate end members and abundances of HSIs. Based on the assumption of end member sharing, we infer the real-world abundances of external RGB datasets. Next, for the sake of conforming to the spatial distribution of practical scenes, we synthesize the various abundance maps via a fusion-based generative model. Finally, we fuse the estimated HSI end members and synthetic abundance maps to generate new HSI samples. Noteworthy that the proposed paradigm is suitable for existing widely used generative model, e.g., VAE, GAN, diffusion, rather than limited to a specific type of generative model. In the experiments, we compare the synthetic performance with various algorithms. To sum up, the GMM does not mimic the actual distribution of objects, and the MST++ do not generate new data. In contrast, the proposed paradigm can generate HSI samples with realistic spatial distribution. Specifically, both the GAN and diffusion models have a marked advantage over the VAE. The efficacy of our proposed HSI synthesis paradigm is contingent upon robust unmixing. For symmetric AE, the lack of physical meaning of latent features and the inherent instability of these shallow features restrict the effective reconstruction and generation of high-quality HIS. In contrast, abundance maps present a more effective representation of the spatial distribution of objects, providing a more explicit physical interpretation, achieving high-quality synthetic results with reliable spatial spectral features. The efficacy of our proposed HSI synthesis paradigm is also contingent upon the generation space. Setting 5 end members is the most efficient option. This slide reveals the significance of introducing the fusion process. Due to limited quantity, training with HSI samples alone results in generation outputs monotonous. Introducing more varied and accessible data is to provide rich and realistic spatial distributions. Boosting by such external guidance, the abundance-based diffusion is empowered to learn more robust and accurate feature representation, generating various and vastness synthesized abundance. In an endeavor to broaden the application of our proposed HSI synthesis paradigm, we ventured beyond traditional remote sensing scenarios and incorporated natural scenes into our experiments. The method yields abundance maps that accurately reflect actual spatial distributions and exhibit distinct spectral features. The synthetic HSIs demonstrate convincing visual effects, portraying a variety of natural scenes with remarkable fidelity. Moreover, our study confirms the beneficial impact of synthetic data on classification tasks. This suggests that synthetic data can enhance the diversity and scale of existing datasets, mitigate issues like sample scarcity and class imbalance, and potentially benefit other downstream tasks. Thank you for listening.